Hey guys, welcome back to another video. Today we're going to be going over Lab 3, Black Hole. So, the purpose of this lab was to basically determine the mass of a black hole, as well as the initial velocity needed for a ship to get close to the black hole and leave. The fundamental principles and models that I used were Newton's first law, the momentum principle, average velocity, and gravitational force. And the main result that I got was that the black hole mass was around 8.16 times 10 to the 33 kilograms, and the ship velocity was -4 times 10 to the 7th meters per second in the x direction, and 1.26 times 10 to the 6th in the y direction. So now more into the models, equations, and assumptions I used. So I used Newton's first law, which is basically defined as how an object stays at rest or at constant speed unless acted on by net force. So we can use this to calculate forces and stuff like that. I also use the momentum principle, which is basically about how a force can cause a change in motion as well as what that force depends on. So I use that definition to derive the velocity. And I also use the definition of average velocity to derive the position formula. And I also use the gravitational force formula to calculate gravitational force in my code. So now more into the actual lab. The system and surroundings were basically just the black hole, the planet, and the spaceship, and the initial conditions were just the mass and position of the things we know, such as the star or planet or stuff like that. So now into the code. First, part 1, finding the mass of a black hole. So I edited this to be the mass of the star. This is just the time in seconds per day. And then right here is where we start to edit the code. P initial is equal to the x component of v initial times the mass, and then the y component times the mass, and the same thing for p final. And delta v is just v final in the x component minus v initial in the x component, and the same thing for y component, and then the same thing for delta p. And then for dp dt, we just did delta p, which is in the x component of that divided by delta t, and the same thing for the y component. We use that to find f net. I found what p hat was, as well as the dp dt, or actually d magnitude of p dt, as well as the dp dt parallel. I used that to, I set that equal to the net force in the parallel direction, and then I also did the same thing for the perpendicular direction, which I set equal to the f net. And using that, I was able to calculate what the mass was. And so, after all of this, so after the rotation, I found the mass to be around 8.16 right here. And then for part 2, basically just edited some more code, found what each force is, converted each variable into its code. So, for example, gravitational force is equal to -g mm over magnitude of r squared times r hat, and we just converted that into code. And after converting all of this into code, we applied the motion equations as well, and then I just tested different velocities until I got a velocity that would bypass, that would get really close to the black hole and then bypass and prevent, like, not get hit. Yeah. There weren't really any similarities and differences because this is just coding. Sources of error, not really any, because this is just code again. So to answer the what does it mean question, there's not really a difference between the rate of change of momentum, and its parallel and perpendicular components, and the net force and its parallel and perpendicular components, because those things are equal to each other. And then for the what if, so what velocity you need for the spaceship to enter into orbit around the black hole, I plugged in a bunch of different values, but wasn't really able to get that to happen. But I tried my best. Yep.